All right, so here got the notes for section 5.3, which deals with connecting the first derivative and the second derivative with the graphs of the original function. So first we have the first derivative test for local extrema. So it gives us some crazy generic equation, mark some points off here. So if you notice any place the graph is rising, we have positive derivatives. And any place the graph is falling, so there and there and there, we have negative derivatives. And at any maximums, we have either zero derivative or undefined. We also have these points here called shelves, where the derivative is zero as well. So the first derivative test says the following test applies to a continuous function f of x. So at a critical point c, if f prime changes sign from positive to negative at c, then you have a maximum because that means the graph is rising, then falling. If f prime changes from negative to positive, you have a minimum, the graph is going down, then up. Because remember, the derivative is the slope. So if you have a negative slope, that means the graph is coming down. If f prime does not change sign at c, then f has no local extreme value. Now remember, to find the critical values, those occur where the derivative is equal to zero or where the derivative is undefined. So we have to find those locations first. Now, if we have a interval or a closed interval or open, we're not looking at the whole graph, we do have to worry about the endpoints. At a left endpoint of a, if the derivative is negative, for x more than a, you have a local max. If the derivative is positive, when x is more than a, then you have a minimum. So what that means is the first one, if the derivative is negative to the right of a, that means the graph is falling, which means that a was a maximum value. It was dropping away from a. If the derivative is positive to the right of a, that means the graph is climbing if you start at a, which means you have a minimum there at a, so the graph's going up. At the right endpoint, they're reversed. So if your derivative is positive to the left of b, that means the graph is climbing. That means b is a, well, I did it backwards, maximum. If your derivative is negative to the left of b, meaning it falls towards b, that means b is a minimum value. So we'll look at that in some of these examples coming up. It's a little bit easier to see graphically necessarily than with words. Okay, so example one, for each of the following functions, use the first derivative test to find the local extreme values. Identify any absolute extreme values. Okay. So actually, is there a typo? Let's see if that's a typo. It should be negative x cubed, or if it should be equals x cubed. So let's find example one. That should be equals x cubed. So that should be an equal sign. There we go. Okay. So to the first derivative test, we take the first derivative, which gives us 3x squared minus 12. So that's the first derivative, and then we set this equal to 0 and solve. So 3x squared is equal to positive 12. X squared is equal to 4. So x is positive minus 2. Remember, if you take a square root, you have to do both values. So then on the number line, we're going to mark our critical values, and we're going to check the value of the derivative. So we're going to plug some number here. So we'll do like x equals negative 3 into the derivative, some number here like 0, and some number here like positive 3. So I need to find f prime of negative 3, f prime of 0, and f prime of positive 3. So if I plug negative 3 into my derivative equation, that becomes negative 3 squared is 9, 3 times 9 is 12, or 3 times 9 is 27, 27 minus 12 is 15. So this is positive. At 0, 0 squared is 0, 3 times 0 is 0, 0 minus 12 is negative 12, so this is a negative number. And at positive 3, we're actually going to get 15 again, so positive. Just as a note, the actual value of these numbers doesn't matter. All I need is positive or negative. Now, so this is the sign chart for the derivative. What that means is that it tells you what the graph is doing. So the graph is climbing until it reaches x equals 2, and then it falls, and then it climbs. So this would be like the generic shape of the graph. And it switches at negative 2 and positive 2. So that means here at negative 2, we have a maximum because it's a peak. So at x equals -2. There's a maximum. We can do the similar thing over here. At +2, the graph falls and climbs. So when x is +2, we have a minimum. Now it says identify any absolutes. We don't have absolute max or mins because this graph falls forever and climbs forever. So even though this is a maximum, it's not the largest value that the graph will take because it keeps going up forever. Even though this is a minimum, it's not the smallest value the graph will take because it keeps falling forever this way. Okay, so now we got this guy, so we'll need to find our derivative. I'm actually going to distribute first because I want to. So there's that. So that's just doing the distributing. So to prime g prime, so this part here is product rule. So 2x e to the x, derivative of the first, leave the second alone. Then it's going to become plus x squared e to the x. And then I remember e to the x is its own derivative. So this would simplify as 2x e to the x plus, oh, I don't know why I'm rewriting this. Nothing, I thought I had some like terms, but I don't. So anyway, what I can do though is factor in e to the x out of all these terms. So that leaves me, I'm going to reorder this, x squared plus 2x minus 3, and set that equal to 0. So this can be factored. Two numbers that multiply to -3 and add to +2, or +3 and -1. So this is the equation that I have. So to find the critical values, I need to solve this. So either this is equal to 0, or this is equal to 0, or this is equal to 0. So these two are relatively straightforward, -3, +1. To solve this, I would take the natural log of both sides, which cancels the e out, so x equals ln 0, but that doesn't exist. You can't take the natural log of 0. So my only critical values are at -3 and +1. Oops, -3. So I need to choose some number over here. So I need to find, we'll say, f prime of -4. I need to do f prime of 0, and we'll do f prime of 2. Now I'm not going to write my numbers down. I'm just going to figure out the sign. So if I do -4 into my derivative, let's see here. So e to any power is going to be a positive number, so I can ignore it. So I just need to worry about this part. So -4 squared is 16, so that's 16 minus 8 minus 3. So that is a positive number. When x is 0, that's 0 plus 0 minus 3, so that's a negative. When x is 2, that's 4 plus 4 minus 3, so that's positive. So this graph has a similar pattern, climbs to 3, then falls till x is 1, then goes back up. So we have at x equals -3, we have a maximum. At x equals 1, we have a minimum. So there we go. There we go. Okay. So concavity. Oh, sorry. There's one thing. This value is actually an absolute minimum because as x gets smaller and smaller this way, the function actually flattens out, so it approaches 0 as x gets more and more negative. So there's a horizontal asymptote, which means this value here at 1 is as far down as the graph goes. It actually has a Anyway, all right. We can also talk about concavity. That's essentially the way the graph opens. So like this parabola is concave up. This shape is concave down. You can actually combine the two. So if I have a graph that looks like this, I have one part here that's concave down and one part here that's concave up. And where it switches is referred to as an inflection point. So for the concavity test, you take the second derivative because you need how the derivative is changing. So you're concave up on an interval where the second derivative is positive, concave down where the second derivative is negative. So it's going to work like the first derivative test, except we're going to use the second derivatives. So use the concavity test, determine the concavity of the given function on the given intervals. Okay, so what that's going to look like is, so I need y prime, it's 2x. I need y double prime, which is 2. So my number line, I'm only allowed to look between 3 and 10 from my interval here. So this is positive, which means, so if I try to set this equal to 0 and solve, I don't get any values. There are no zeros in here. This is positive, so this graph is concave up everywhere on that interval. So it's concave up on 3 to 10. So similar thing here. So first derivative, that goes away. Derivative of sine is cosine. Second derivative would give me negative sine x. So number line, I'm only looking between 0 and 2 pi. So I need any place that the sine is 0 between 0 and 2 pi. Let's see here. So where is the sine 0? The sine is 0 at 0, it's 0 at pi, and 0 at 2 pi. So I need to plug some number between 0 and pi in, like pi over 2. So double prime at pi over 2. So the negative sine of pi over 2 is negative 1, so that section is negative. And over here we'll do 3 pi over 2. So the negative sine of 3 pi over 2 is actually positive 1. So this graph is concave up, where it's positive, between pi and 2 pi. And it's concave down, where it's negative, between 0 and pi. And if you think about what the sine curve does that shape. So here's 0. That's a really bad drawing. We'll come over here. So there's 2 pi, there's pi. So concave down is part of a downward opening parabola, concave up. Okay, so we talked about, I mentioned this before, a point of inflection. This function has a tangent line, a point where the graph of a function has a tangent line and where the concavity changes is the point of inflection. So here at pi, the has a tangent line means it also has to be continuous. So find all points of inflection of the graph y are equals, so we need the first derivative. So to take the derivative of e, it's the derivative of the exponent times the original equation. And then to get the second derivative, that's now product rule. So negative 2 ex2 plus negative 2x times negative 2x e to the negative x squared. So negative 2 e to the negative x squared. That's going to be plus 4x squared e to the negative x squared. So I can factor a negative 2e to the negative x squared out, which leaves me 1 here, which leaves me negative 2x squared here. I took a negative 2 out, which is why I changed signs. So I have that. So I need to know where is this equal to 0. So I have to solve this guy, and I have to solve this guy. So this is going to be negative 2x squared equals negative 1. So x squared equals positive half. So x is equal to the square root of 2 over 2. Or 1 over root 2 if you want to do it that way. Plus minus. Over here, e to the negative x squared is equal to 0. Take the natural log of both sides. So this is undefined because you can't take the natural log of 0. So my number line, I would mark off negative root 2 over 2. Oops, off the screen. And positive root 2 over 2. And then choose values. So for example, I could put 0 in. So this root 2 over 2 is about 0.7. So I can do f double prime of 1, f double prime of 0, f double prime of negative 1. So if I plug 1 into my second derivative, I get negative 2 times negative 1, so I get a positive number. If I plug negative 1 in, I get negative 2 times, so negative 1 squared, so it's going to be the same thing, it has to be positive again. If I plug 0 in, I get -2 times 1, so I get negative. So I have two inflection points, one at negative root 2 over 2, one at positive root 2 over 2, because that's where the things change sign. So those are my, it says points of inflection, so I actually need to find the ordered pair. So negative root 2 over 2, comma, something, and positive root 2 over 2, comma, something. To find those somethings, you plug back into your original equation. So let's see here. So it's actually going to be the same values because I'm squaring. So root 2 over 2 squared is 1/2. So it's e to the negative 1/2, which is the same thing as 1 over root e. So those would be the 2 points of inflection, where it changes from concave up to down here and down to up at the second one. Okay, so example 4 here says the graph of the derivative, so this is actually graphing f prime on the interval -4 to 4 is shown. Answer the following questions about the original function, which we don't know anything about other than its derivative. Okay, on what intervals is f increasing? So the original function increases wherever it has a positive slope, which means wherever the derivative is positive. So the derivative is positive between -4 and 1. So from -4 to 1. So that interval, or if you want -4, less than x, less than 1, if you want the inequality notation. On what intervals is the graph concave up? So we're actually looking at the slope here. So concave up means the second derivative is positive, which means the slope of the derivative equation is positive. So that occurs between -2 and 0, and between 3 and 4. So because the derivative rises here, so -2 to 0, and from 3 to 4. At which x coordinates does the function have local extrema? So that's where the derivative changes sign. So there's only one of them here at x equals 1. There's only, oh, sorry, bad example. There's actually two other ones. Since we have a closed interval, the endpoints will also be local extrema. So here the graph has a positive slope. So this -4 here is actually a minimum because it has a positive slope. So at -4, the original graph is actually climbing because the slope is positive. Here at +4, the slope is negative to the left of it, so the graph is falling towards 4, which makes +4 also a minimum. At x equals 1, I have a positive slope to a negative slope, so the graph rises, then falls, which means this is a minimum. The x coordinates of all the inflection points. So that's going to be where this equation or this graph changes direction. So where it goes from positive slope to negative slope. So at -2, at 0, and at 3. So those would be the inflection points. And sketch a possible graph on the interval. Okay. So let's look at a graph here. So 1, 2, 3, 4, 1, 2, 3, 4. So it has to increase from -4 to +1. Right. Oops, I wrote that wrong. That's not a minimum there. That's a maximum. There is a point here where the derivative goes to 0, which means I'm going to have a little shelf there at -2. So like the graph would rise, kind of flatten out, then start to rise some more until it got to x equals 1. And then the slope comes down, and then x equals 3. The concavity has to change, so it has to do something like that. So this section here is concave up, and that section there is concave down. So, or sorry, reversed, down and up. It's a bit sloppy. It's hard to do, but that's the general idea. Okay, example 5 here. So we've got a particle moving along the x-axis with position function 2t cubed minus 14t squared plus 22t minus 5. When t is 0, find the velocity acceleration. Describe the motion of the particle. Oh, this is a throwback. Okay. So if x is our position, our velocity is the first derivative. So that's 6t squared minus 28t plus 22. The acceleration is the derivative of the velocity, so it's the second derivative of the position. So that's 12t minus 28. So let's see here. To describe the motion, so you essentially just look at the three graphs here. So this function here, the velocity, so when t is 0, so the velocity at 0 is 22, but this parabola opens up, so it's going to go down and then come back up, so it slows down and then speeds back up. The acceleration, this object is slowing down. We're getting a more negative acceleration, so at t equals 0, it's speeding up. The acceleration is climbing, which is why the graph changes. So if you do the velocity function, it looks like this. So this slope is always getting more and more positive. It starts negative, gets closer to 0, and then becomes more positive. So there's my velocity curve. It's a parabola, which means that the position function is a cubic. So it looks something like that. Okay, second derivative test for local extrema. So you can use this if you don't want to use the sign chart for finding, what am I talking about? For finding max or mins. You can actually, so you find the critical value still using the first derivative, but then you plug those critical values into the second derivative. That should be a double hash there. And look at the sign of what you get. If the second derivative is negative, you have a maximum. If the second derivative is positive, you have a minimum. So what that looks like is this. So we need f prime. So that's 3x squared minus 12. So I'm going to set this equal to 0. So that's 3x squared is equal to positive 12. X squared is equal to 4. So x is positive minus 2. And then I'm actually going to take the second derivative, which in this case is 6x, and I'm going to plug my critical values in. So f double prime of negative 2 is going to be 6 times negative 2, which is negative 12. That number is negative, which means I have a maximum at x equals negative 2. F double prime of positive 2 is going to be 6 times 2, which is positive 12, which means I have a minimum value at x equals 2. So without having to do a sign chart, you can do it that way. I honestly prefer the sign chart, but that's just me. Okay, 7, let the derivative equal 4x cubed minus 12x squared. Identify where the local extrema occur. So we need to set our equation equal to 0 and solve. So I can factor a 4x squared out, which leaves me x minus 3. So at x equals 0 and at x equals 3, we'll have local extrema at 0 and at 3. Let's see here. So we'll go to our number line for increasing, decreasing. So we mark 0 off, we mark 3 off. So we need f prime of some number less than 0. We need f prime of some number between 0 and 3. And we need f prime of some number more than 3. So I'm using my derivative function. So when I have negative 1, that's always going to be positive. That's going to be negative when x is negative 1. So positive times negative is a negative section. At f equals 1, I have another negative section. And at 4, I finally get a positive section. So this graph, now since this is a 0, this graph falls, levels, falls, and then climbs. Would be the original function. So here at f 0, I don't have a max or a min. At 3, I have a minimum value. Use a sign here. The derivative sign doesn't change at 0. Find where the graph is concave up and where it's concave down. So that means I need the second derivative. So f double prime. So now I already have the first derivative. So this is going to be 12x squared minus 24x. I'm going to set this guy equal to 0. So I can factor a 12x out, which gives me x minus 2. So at x equals 0 and x equals 2. And those numbers go on my number line. So f double prime of -1, f double prime of +1, f double prime of 3. So if I'm plugging into this equation, when I use -1, I get -12 times -3, that's positive. If I plug 1 in, that's 12 times -1, that's negative. If I plug 3 in, that's 36 times 1, that's positive. So this graph is concave up from -infinity up to 0, and then from 2 to infinity. It is down between 0 and 2.
That little cup symbol there means the combination when you're joining the two together.
So a possible graph, well, I kind of actually already sketched it here, didn't I? So we're concave up till 0, then we are concave down, so we fall a little bit. Then at 3, we have a minimum. But at 2, we change, so something like that would work. Okay, example 8. So a function f is continuous on the interval -4 to +4. Discontinuous function f prime with domain given here. So if you notice, it breaks at 0 and breaks at 2 because there's open circles there, so it's not included. It's shown below. Find the x-coordinates of all local extrema. So local extrema are where the derivative changes sign. So there's one at -3 right there. There's one at -1 right here. There's actually one at 0 because the derivative is positive and negative. And there's also one at 2, positive to negative. So there's my x-coordinates of all my extreme values. Sketch a possible graph. Okay, so let's see here. So at 0 and at 2, I am going to have a corner or a cusp because the derivative doesn't exist. Over here, the derivative is constant, which means I'm going to have a straight line section. And it's negative, so it's going to be coming down. So that piece is because of that slope. So let's see here. The derivative is positive, then it's negative, so I've got kind of like a dippy looking thing here. And then, let's see here. So the derivative is positive, so the graph has to be rising, and then it has to be falling. So there's falling. So that's the negative section, then it comes back up, so something like that. But that's a really hot mess. Anyway, it's got to come back down too. So the graph has to be rising. So rising, so here is -3. Then it falls. Here is -1. As it rises, and then switches, negative slope. All right. And that brings us finally to the end of the section.